Hello everyone, this is the first lecture video for economic statistics for fall 2023. So this semester, as you know, we are moving from Blackboard to Brightspace, and I am quite struggling to set it up. Like I built a lot of course materials on Blackboard, but I have to relearn everything, and so it takes more time than I expected. So please understand. I'll try my best to set it up and make it as clean as possible, as scheduled. But in case if I couldn't, please understand, right? And okay. And by the way, I am doing this online, and I did it online for the past couple of years. So in case if you think my lecture video is not enough, then you can also watch previous year's videos. Basically, I'm using the same slides, basically the same thing, but I may like rephrase, or I may say something that I did not say last year, or vice versa. So if you want to repeat, but if you don't want to do exactly the same thing, then you may watch the last year's video. And all of the videos are available on my YouTube channel. So I believe it's not that difficult to find that out. Just go down the list of videos, and then you can watch more videos from the previous years. Okay. So it's chapter 1, which is about probability. So probability, everyone knows what is a probability, but the goal of this chapter is to define the structure of probability, right? So to understand probability statistically, we have to define that mathematically, okay? So to give you a broad overview of this class, or this course, uh, as I said in the introduction, there are 12 chapters, and the first 4 chapters would be about descriptive statistics. This is basically about how to summarize, how to describe data, right? And the next 4 chapters, like 5, 6, 7, 3 chapters, are distribution models. The models, the difference between description and modeling is that a modeling makes assumption, right? So description is just a description. So I don't make any assumption and just describe what's going on, right? Like calculating the mean, calculating the probability. That is description. I don't need any assumption. But in modeling, we utilize assumptions. For example, I assume that something is normally distributed, and then we can study more about that data. So that's the key difference between first part and the second part. And then, so up to this point, the first 2 parts, first 7 chapters, are basically like a mathematical analysis of randomness, distribution, probability. But what we actually use in practice is inference. That is different. We have to analyze, we have to understand how the randomness is generated, what kind of properties they have, and then using those properties, we are going to apply them to our inference. So given the data, we would like to know the underlying randomness, and then how can we make the best inference, or what is the expected inference errors, or what's our, like, for example, the many statistical terms will be introduced in this part, like confidence interval, like standard error, like p-value, t-statistics, hypothesis testing. These kind of more practical statistical tools are about inference, which we discuss in the third part of this course. And finally, in the last 2 chapters, I will introduce linear regression model. Linear regression is a kind of inference, but it is widely used in economics and in many social sciences. So uh, the the reason why this course is a required course for econ major is because you have to understand linear regression uh, in order to understand more advanced courses like industrial organization, international trade, labor economics, monetary economics. In those applied economics, they utilize data, and then the the maybe 90, the more than 90% of the data analysis is based on linear regression. So, understanding linear regression is the ultimate goal uh, of this course, and this is the reason why you are required to take this course. and if you and the next course, ECO420, if you are more interested in data analysis, then you are going to take 420, and that course is basically extension of the basic linear regression that I'm going to introduce here. So there are many variants of linear regressions. So that's going to be the main theme in the following data analysis course. So that is an overview of this course, and of course we are going to start from here. In the first part, as I said, is about description, right? Remember, it's about description of data, which is basically to understand, to characterize randomness. And there are two main building blocks in those in describing data. One is probability, the other is average, right? So you know everything about them. So I'm going to just make them more rigorous. I will approach to them more rigorously, more mathematically, and think about different examples, how they are connected. Like we think of like coin toss, like rolling a dice. But how are they related to like our stock market data, our like wage income distribution data? So seemingly they are not related, but we use the same terms like probability, average for both of them. Like in statistics, we only consider coins, but in reality, we have to think more general, more complicated data. So to connect them, first we have to understand the fundamentals behind them, behind the randomness. That's basically not that difficult, probability and average. So I'm going to discuss them. Let's see. And relevant chapters if you need reference. And by the way, I don't require textbook. You don't need to buy that. Buy any textbook. But if you want, and if you want me to recommend one, I found this textbook this year. I didn't know this textbook like last year. So and I like it a lot. So Vital Statistics is the textbook that I recommend, and if you use that, then you can find the same topic in here. But basically, what I teach is not new in any sense. It's been statistics has been developed like 100 years ago, so nothing is special, nothing is different from the textbook. So you may use any textbook. Basically, they will be the same thing. So this is what I'm going to do. Let me start from the first part, structure probability. So we will again, as usual, as any statistics course does, we are going to start from the very simple, the simplest possible probability description. When you toss a coin, the probability of a head is 50%. So this is a simplest possible probability sentence. In this sentence, we are going to analyze this. You understand what it is. We have to understand there are some components, basic, important components to construct a complete probability. first is the probability itself. So 50%. This is obvious. So probability number is not a big problem. But also we have to think about the other components. Like if you say 50%, it's not a sentence. It does not mean anything. To complete a sentence, you have to have other components like this. Toss a coin. When you toss a coin, means this specifies the experiment, the random experiment that generates the randomness, right? Like when you think about probability, you have to know where the randomness is coming from. What are you doing? Like if you toss a fair coin, it's 50%. But if you toss something like different from a coin, probability could be different, right? And also, you have to define the event you are thinking about. So 50%. When you toss a coin, 50%. The probability is 50%. That is not complete because you have to say when you toss a coin, probability of what is 50%, right? In this case, head is the event of interest. Uh, so you are attaching the probability to this event. So these two concepts, experiment and events, are the main subjects of this chapter, right? Right. So just to define them, define some basic terms. Experiment is a process that generates randomness, that leads to a random outcome, right? But you don't need to memorize this definition. You know what is an experiment, right? An outcome is an outcome, right? A result from an outcome. I don't need to define this, but just to make sure this outcome is exactly the same outcome you have in mind, I'm just writing this. Sample space is more like it's not a casual phrase. Sample space is the collection of all possible outcomes, right? So this is statistical term, but experiment and outcome are exactly the same meaning as you use. In coin toss example, there are only two possible outcomes. The experiment is tossing a coin, and then two possible outcomes are heads and tails. And the sample space is the collection of these two outcomes. Simple, right? And let's think about the sample spaces from different experiments. If you roll a dice, sample space is 1 to 6. If you are like a quality control manager, and then when you inspect some part, and then the outcome is either whether the part is defective or not. If you check a semiconductor, if it's working or not, then it's working or not, something like that. And if you play a game like rock, paper, scissors, then the outcome is win, lose, or tie, right? So there are three. And if you do a customer survey with answers, with binary answers like are you satisfied or not, then the outcome is satisfied or not. But it depends on your questionnaire. If you ask your customer to choose from 1 to 5, then the sample space will be from 1 to 5. But if you ask your customer with the option from 1 to 10, then the sample space will be different. So anyhow, the outcome is the collection of all possible outcomes is the sample space. And household income survey, in this case, like how much is your household income? Then the possible answer is any non-negative number. Like my household income is $1,000 or like $1 billion. Any number is possible. So that's the possible outcomes. So these, depending on the experiment, we think of different sample space. So it's pretty obvious. And then probability is defined this way. the proportion of times that an event occurs when an experiment is repeated many times. So this is the probability you know. When you repeat an experiment many times, you are going to get a certain event, like several times, proportionally according to the probability. That's the proportion is the probability. And here, related to this, so the point here I want to emphasize here is repetition. When we define a probability, we implicitly assumes that we are hypothetically repeating the experiment, random experiment, right? That is the key point to understand probability. And then data is just a set of the collection of observed outcomes from repeated experiments, right? Data is like if you toss a coin and repeat that 10 times, then you have a data of 10 observations. That's data. Sample size is the number of repetitions. So if you toss a coin 10 times, sample size is 10. You observe 10 outcomes. If you repeat 100 times, you observe 100 outcomes. That's the sample size. So repetition is pretty important in statistics. Maybe the most important thing in statistics is the sample size, because this determines the accuracy of your analysis. Statistical analysis is basically determined by the sample size. Like if you have a huge sample size, then you can do almost anything. But if you have a small sample size, then you cannot do anything. So sample size sounds too obvious, but basically that is the most important determinant of the quality of statistical analysis. However, in many cases, we cannot change the sample size. It's given. We cannot generate more data. So usually, it's given like and maybe increasing the sample size also requires huge cost. So due to like just maybe like experiment structure or financial constraint, the sample size is limited. That is the starting point of statistical inference. Given a limited sample size, we would like to understand the whole sample space. That is what we are going to do in the long run. So here is an example. So think about coin toss again. So we already know that coin toss is a very weird example because we know the true probability. True probability of heads is 50%. But you know, even if you throw a coin like say 100 times, it is not exactly 50 times you see heads. You may see more than 50 times, like 51, 52, or 49, or 48. It's possible in your data. That's mainly because you are not doing enough repetitions. So this is computer simulation of coin toss. So when I throw the coin one time, it's either 100% or 0%. Here I happen to get head for the first trial, so I had 100%, and it drops to 50% and then moves up and down. Blah, blah, blah. It like oscillates around 50%. But what you can see here is it may deviate from the true probability. Like true probability is 50%, but at some point it goes down as low as nearly 40%. So about 10% point is the random error. This random error gets smaller, diminishes as you increase the number of repetitions. So large sample size will guarantee more accurate analysis, right? So if you can increase it even more, then nearly the random error will be very, very, very small. It will be like 50.00001%, for example. So that's the power of sample size. And also, what you have to understand here is then you can think about limit, right? That's population. Population. So what you want to know in the end is when the sample size increases to the infinity, the mathematical limit, that is called population. So population is the collection of all items of interest. To observe all items, we have to have infinite number of repetitions, but that is not possible. So our sample is observations, finite observations, which is just a part of the population. Basically, that means data. Data is just part of the whole population. And from here, I will suggest you to understand this as n equals to infinity. So population is the limit. Your data is given, and if you could increase the number of repetitions, you will get larger data. And if you can do infinite number of repetitions, in the end there must be some limit. The limit is population. That is what we want to know. In mathematically, we would like to know the limit, but it is not possible. So we have only part of that. And then, as you can see, the probability we calculate from just a part of the population can be wrong. But in the limit, it will converge to the true probability. In other words, the true probability is defined as the probability when you can repeat the experiment for infinite number of times. That is statistical inference. From the finite sample, we would like to understand infinity. That is what we are going to do. Okay? So, already it's been 22 minutes. I will stop here. This is the first video. And as I said in the introduction, I am going to continue in another video. So you may go to the bathroom and you may stop here and watch the next video tomorrow. It's up to you. So flexibility is the biggest advantage of doing online learning. So I hope you enjoyed this video, and I really hope you watch the next video soon. See you later.